And now we make the following claim. Let's call it claim 1, which states that all the vectors in lambda sub w have lengths bounded away from 0 by a uniform amount, and this may depend on D and S, but independent of lambda. First thing we want to note is that this claim is quite independent of our rescaling, because when we rescale lambda sub w, the constant we use for rescaling only depends on D and S. But here we only need this quantity to depend on D and S, independent of lambda. So anyway, it doesn't matter if we rescale lambda sub w or not. And we will prove this claim by contradiction. Indeed, if not, then there exists a vector, a lattice point in lambda, such that the norm of the projection of x onto w, which by the formula is equal to x minus the dot product of the unit vector along b1 and x, this scalar times b1, pi w sub x is equal to x minus this scalar multiple of b1. And this, so suppose this claim fails, then we will have a non-zero vector x such that this quantity is less than half of s, which is less than half of b1, because we assumed at the beginning that b1 is greater or equal to s. Now we consider the following function. The closed integer to a number alpha. This is a closed integer to a real number alpha. We know for every real number alpha, the difference between alpha and the closed integer to it is always bounded by 1/2. So if you draw a picture, this is a real line, this is alpha, and you consider the closed integers to alpha, you have the floor of the alpha on the left and the ceiling of alpha on the right. But anyway, one of those two distances must be less than or equal to 1/2. That is what I want to say. And now let's see how these give us a contradiction. We consider the norm of the difference between x and the closed integer of this quantity multiple of b1. And by the triangular inequality, this is bounded above by the difference between x and this scalar multiple of b1 plus this guy minus the closely integer part of this number times b1. And you know by our assumption that this first part is strictly less than the norm of b1 divided by 2. And the second one is less or equal to norm of b1 divided by 2. Because of this relation, because of this inequality, alpha minus the integer part of it is always bounded by 1/2. That's exactly what's going on in here. So after all, this is strictly less than the sum of these two, which is norm of b1. But this is a contradiction. Do you see why this is a contradiction? This is a contradiction because b1, we assume the b1 be the shortest non-zero vector of lambda, and now we have found an even smaller point highlighted here that is in lambda, because x is assumed in lambda, and this integer multiple of b1 is also in lambda, so their subtraction is in lambda. The norm of this guy is even smaller than b1, which is a contradiction. And this contradiction proves our claim that all the vectors are bounded away by the uniform amount. Now let's make the second claim. The claim says we can find a basis of this projected down of this lambda sub w satisfying the following two things. First, the lengths of the vectors in this basis are uniformly bounded away from infinity. And secondly, this basis of lambda w can be lifted to complete the basis, say b1 the bd of the original unimodular lattice lambda, with each basis vector has norm or length bounded by some constant that only depends on d and s for all j. And I should remark that this claim, the claim 2, implies our super claim at the beginning, because remember we want to find the basis in lambda that belong to a given ball of radius depend only on s and d. This is implied by the part 2 of our claim 2. And part 1, together with our claim 1, says that each vector in lambda sub w is both bounded away from 0 and from infinity by a uniform amount that only depends on d and s, independent of lambda. And that is the significance of our claim 1 and 2. And now we shall prove our claim 2 inductively. What we will first do is that we will apply our previous argument. Specifically, we're going to apply our argument in here. Remember that argument in here gives us an upper bound for the shortest vector in lambda. And that upper bound only depends on d. But now, because of the rescaling of lambda sub w, the new upper bound for the new shortest vector in lambda sub w will depend on d and s. So by the previous argument applied to the rank d-1, and after rescaling unimodular lattice lambda sub w, we have the following. If we take b2 prime in lambda w such that b2 prime has length the shortest among all non-zero vectors in lambda w, then we have the norm of b2 prime is bounded above by a constant depending on d and s and independent on the choice of the lattice. Previously, this upper bound only depends on d, and now it may depend on s because we rescaled this lambda sub w so that it is unimodular. And notice that this also has a lower bound that only depends on d and s. The reason that we have this lower bound is because we proved in our claim 1 that all vectors in lambda w has length bounded away from 0 by a uniform amount. So this lower bound follows from the claim 1.